Here's a chance to see how well you understand bridge functionality. The bridge has just received the frame shown on screen on port 2. What will it do now? Type into the MAC address table to make any necessary additions. Then select each action the bridge will take. When you are finished, click Submit. Not quite. Try again. That's still not right, because source address 0001.0002.1234 is not yet in the MAC address table. The bridge will add it to the table as a device on port 2. The MAC address table uses source addresses, not destination addresses, to build its data. So, the destination address will not be added to the table. Because the destination address is not in the table, the MAC address table does not yet know that the destination device is on port 3. So we will forward the frame to port 1 and port 3 in case the destination device is on either of those ports. Click Continue to move on to the next. Bridges were huge advances in the development of Ethernet LANs, but they weren't perfect. Often, bridged network segments were interconnected to create redundancy so that if a failure occurred on one segment, data could be sent by another route. But when there are multiple paths in a bridged network, loops can form. When a bridge receives a frame, it updates its MAC address table with the source MAC address. If it doesn't have the destination MAC address in its table, it floods the frame out every other port. In this case, both bridge B and bridge C receive the frame and update their MAC address tables. Bridge B doesn't have the destination in its table, so it forwards the frame out all ports. Bridge C doesn't have the destination in its table either, so it also forwards the frame it received on port 1 out all ports. But now bridge C has the frame it just received on port 2, and bridge B has the frame it received on port 3. They both update their address tables accordingly, and then flood the data out all ports, except the port on which the data was just received. Bridge A receives data on port 3 and port 2. If it received the data on port 3 first, it will update its MAC address table to show that port, and again flood the data out all other ports. And then bridge A will update its MAC address table again to show that data arrived on port 2, and again flood the data out all the other ports. As you can see in this scenario, the address tables are constantly changing, and the simple bridge forwarding rules we just discussed have created a forwarding storm, where the same frames are forwarded endlessly in a loop. Broadcast and multicast traffic can create this same issue. Remember that if the destination MAC address is a broadcast or multicast address, a bridge must always forward it out every other port. When a network has loops, bridges receive broadcast traffic and rebroadcast it out all ports again and again, creating what is known as a broadcast storm. A broadcast storm can block all other network traffic and bring a network to a complete standstill. We don't show it here, but as we saw in the previous scenario, each bridge must also keep updating its MAC address table each time it receives the same frame on a different port. To prevent loops, bridges use the Spanning Tree Protocol, or STP, which selectively disables bridge forwarding on individual ports to ensure that the network topology is loop-free. Discussion of the Spanning Tree Protocol is beyond the scope of this course. Now, let's look at the devices used in today's networks. Network devices today look nothing like the repeaters, hubs, and bridges used just a few years ago. Instead of a group of devices sharing the bandwidth of a 10 megabit per second network, network devices today get dedicated bandwidth with speeds from 10 or 100 megabits per second up to 100 gigabits per second. That's an increase in speed of 10,000 times in just a few years. You hear network speeds thrown around all the time. 10 megabits per second, 100 megabits per second, 1 gigabit per second. These speeds all sound very fast, but what do these terms really mean? And more importantly, what do they mean to you the next time you need to transfer a file? Network bandwidth, also known as the data transfer rate or bit rate, is the amount of data that can be sent from one point to another in a given time period, usually 1 second. Network bandwidth is usually expressed in bits of data per second, which is abbreviated BPS or bits/s. Notice that it is bits per second, not bytes per second, which would be represented with a capital B. Network bandwidth can be thought of as the maximum capacity of a network connection. Throughput, on the other hand, is the actual amount of data that can be sent over a network in a given period of time and is a more realistic measure of performance. For example, a fast Ethernet network has a network bandwidth of 100 megabits per second, but the actual throughput might be around 80 megabits per second due to network overhead as well as hardware and software bottlenecks. Because of technological advances, network bandwidth continues to increase almost exponentially. The table on screen shows how larger bit rates are expressed using the International System of Units symbols before the unit of measure. For example, 1,000 bits per second is the same as 1 kilobit per second or 1 kbps, and 1 million bits per second is equivalent to 1 megabit per second or 1 mbps. Early Ethernet networks provided the end user and network devices with data transfer rates of 10 megabits per second. This bandwidth was shared by all devices on the collision domain. With the introduction of Ethernet switches, these transfer rates increased to 100 megabits per second and can be dedicated to a single device. So what does that mean on a practical level? On screen, you can see how long it would take to transfer a 1 megabyte file using 1 megabit per second, 10 megabit per second, and 100 megabit per second connections. You can see it would take 8 seconds to transfer 1 megabyte using a 1 megabit per second connection. If that seems confusing, remember that file sizes are measured in megabytes and connection speeds are measured in megabits. Since there are 8 bits in a single byte, we have to divide the bandwidth by 8 to get the number of bytes per second that we can transfer. A 1 megabyte file is a pretty small file. In plain text format, about 100 pages of text would make up 1 megabyte. If you want to transfer graphics, file sizes are much larger. To transfer a 50 megabyte file using the same connection would take 400 seconds or 6.6 minutes. If we had a 100 megabit per second connection, it would only take 4 seconds to transfer that same 50 megabyte file. Earlier, though, we mentioned that network throughput is usually lower than the network bandwidth, and even this rate varies. For example, if you download a video early in the morning, throughput might be greater than if you downloaded the same movie later in the evening. Why? Your network connection's bandwidth didn't change. When more people are using the network, though, congestion occurs, packets might get dropped, and network throughput slows down. So let's take network throughput into account and see how long it might take to transfer the same 50 megabyte file. If we assume that we only get 80% of the network bandwidth, it might take approximately 500 seconds or 8.3 minutes using a 1 megabit per second connection and 5 seconds using a 100 megabit per second connection. As networks grew, network devices needed even more capacity to support more users with higher bandwidth connections. To provide high throughput, connections between network devices such as Ethernet switches or routers now operate at 1 gigabit per second and 10 gigabits per second. Soon, network devices will need connections capable of transferring data in the terabit per second range. For reference, home internet connection data transfer rates range from less than 1 megabit per second to as high as 1 gigabit per second. What makes such advances possible? The reasons vary and include technological advances such as running fiber optic cables directly to homes and businesses instead of using the plain old telephone line, as well as minimizing the distance to your internet service provider's central office. In this section, we'll see how new devices called switches and routers changed networking configurations and dramatically increased network speeds. Let's recall what we learned about collision domains and half-duplex data transmission. As we learned in the last section, bridges break or segment one large network into smaller collision domains. Because fewer devices are competing for network access, overall network performance improves. However, older devices relied on half-duplex data transmission. That is, a device first had to listen before transmitting to ensure that the network was available. The device also assumed there were many other network devices on the same network segment and therefore had to be ready to deal with collisions. In half-duplex Ethernet networks, after a device transmits data, it listens to the network and expects to hear the same data in the exact same pattern. If the device hears a different pattern, it assumes a collision has taken place. If a device must wait its turn to send data and then cannot send and receive different data at the same time, time is wasted. Waiting and listening takes up valuable network time and makes the network not as efficient as it could be. As we'll see, modern network devices have greatly reduced the chances of collisions and in doing so greatly increased network performance. As we mentioned earlier, end-user devices today connect to network devices using twisted pair or fiber optic cables instead of coaxial cables. Twisted pair wiring offered new possibilities for networking that coaxial cable didn't have. When we take a closer look at the twisted pair wires used in an Ethernet environment, we see that there are a pair of wires for transmitting data and a separate pair of wires for receiving data. The pinouts shown on screen are for regular Ethernet end-user devices such as PCs, servers, printers, and routers, a network device we'll discuss later. Normally, an end-user device connects to a port on a network device, such as a hub or a switch, using a straight-through Ethernet cable. When the end-user device sends data on its transmit pair of wires, the network device receives the data on its receive pins. You can use a crossover cable to connect the two PCs together to share files. A crossover cable swaps the wiring for pins 1 and 3, as well as 2 and 6 on one end of the cable. This swap crosses the wires, so the transmit wires on the sending computer connect to the receive circuitry on the receiving computer. Because there are two different paths, an Ethernet device is capable of transmitting data onto the network using the transmit pair, while it continues to listen using the receive pair. So, in theory, Ethernet networks were no longer restricted to half-duplex data transmission, but could transmit and receive simultaneously. In practice, however, it wouldn't work in a bridged network. In a bridged network, a network can be segmented only so far. Users still compete with each other for network access on the same segment or collision domain. As long as that was the case, collisions would still be a problem. It was still necessary to listen to make sure the line was clear before transmitting data, and after sending data, listen again to make sure a collision had not occurred. To overcome that limitation and take full advantage of twisted pair cabling, the switch was developed. Ethernet switches are similar to bridges in that they are both Layer 2 devices that help manage and control traffic. As with a bridge, each port on an Ethernet switch creates a separate collision domain. Just like a bridge, an Ethernet switch forwards traffic and learns which MAC addresses reside off each of its ports. Where they differ is that Ethernet switches have significantly more ports than bridges. Today, a simple switch might have just a few ports, but an enterprise-level switch can have hundreds of ports. When a single Ethernet switch port can be dedicated to a single end-user device, hubs and bridges are no longer necessary. Because switches dedicate a single bridge port to one end-user device, collision domains have only two devices, the end-user device and the switch. End-user devices no longer compete with each other for network access, and with twisted pair cabling, each transmit pair is an isolated circuit. Because both sides of the connection will receive data from only a single network device, packets will not get corrupted by multiple stations transmitting simultaneously. By isolating each end-user device in its own collision domain, and providing two separate paths to transmit data to the switch and receive it from the switch, collisions are effectively eliminated. Without the danger of collisions, devices can freely transmit and receive data at the same time, which is called full duplex data transmission. Full duplex data transmission is similar to using a telephone, where you can talk and listen at the same time. Ethernet switches with full duplex data transmission offer much greater bandwidth than bridges did. With full duplex data transmission and dedicated switch ports, an end-user device can send and receive data simultaneously, effectively doubling network performance. End-user devices no longer have to share 10 megabit per second or 100 megabit per second of bandwidth with other end-user devices. Finally, in addition to basic Ethernet connectivity, switches make possible virtual LANs or VLANs. VLANs provide a way to break a single LAN into separate LANs on the same switch. Earlier we learned that when a bridge receives a frame with a broadcast destination address, it must forward the frame out every other port. The same is true of switches. Segmenting a network with switches fixes the collision problem, but it doesn't address the fact that broadcast traffic must be sent out all other ports, which uses up precious network bandwidth. VLANs help solve this problem. Here, you see a single switch with two different VLANs identified by color. Essentially, VLANs are a way to subdivide a LAN. A VLAN is a group of PCs, servers, and other network devices that may be connected to the same switch as other devices, but behaves as if they are connected to the same, smaller LAN or a completely separate switch. Devices that are in one VLAN do not receive broadcasts from devices in another VLAN. If a device on the purple VLAN sends a broadcast, the switch sends the broadcast out only the ports configured on the purple VLAN. The switch doesn't send the broadcast out the green ports even though they are on the same physical switch. When devices on different VLANs need to communicate, even if they are on the same switch, a router must be used. We discuss routers in the next section. A more detailed discussion of VLANs is beyond the scope of this course. Switches do have limitations. Because they forward frames just like bridges, they are susceptible to the same sort of network hazards, such as loops, that bridges are. Both switches and bridges must forward broadcast and multicast frames out every port. If there are loops in the network, broadcast and multicast frames can cripple a network. Like bridges, switches also use the Spanning Tree Protocol, or STP, to prevent network loops. Likewise, switched Ethernet networks might not improve performance if a network has a lot of multicast and broadcast traffic. Finally, Ethernet switches might not be able to interconnect geographically dispersed networks. To solve these problems, a different network device, called a router, is required. Whereas Ethernet switches operate at Layer 2 and can examine only the destination Layer 2 or MAC address, routers operate at Layer 3 and can examine Layer 3 addresses. In our next section, we'll examine the difference between Layer 2 and Layer 3 addresses, as well as router operation. We wouldn't be giving a true overview of today's Ethernet networks without discussing wireless LANs. As the name suggests, wireless LAN technology allows the extension of an Ethernet LAN segment without the need for cabling. You can think of a wireless LAN in much the same way as we have discussed a wired Ethernet LAN. The primary differences are the equipment. Instead of using an RJ45 NIC to connect to a switch, wireless clients use a wireless NIC, which has a radio built into the device to connect either directly to a switch or through a wireless access point, which subsequently connects to a switch. Let's take a look at three common wireless LAN architectures: the autonomous architecture, the centralized architecture, and the distributed architecture. The first type of WLAN architecture, autonomous architecture, is known as FAT access point or FAT-AP architecture, where all functionality is coded into every access point or wireless termination point. Home networks today often make use of the autonomous architecture in the form of a single FAT access point. The second type of WLAN architecture, centralized architecture, is known as a switched WLAN system. In this type of system, the access points become thin or lightweight, and there is a central switch or access point controller that actually manages them. Most enterprise networks today choose this centralized or switched WLAN model. The primary reason for this is scalability. The autonomous WLAN architecture is impractical in an enterprise setting. In an enterprise setting, you may well require hundreds or even thousands of access points, and if each one must be managed individually, it quickly becomes unworkable. With a centralized or switched WLAN system, the access point controllers are the managed devices. This reduces the management problem by at least a factor of 10. Switched WLAN systems are physically more secure than other architectures. The access point controller may be installed in a locked data closet or data center, and the thin access points are a less likely target for theft, as without the controller, they can't be used. In addition to this, these access points typically don't store any configuration data or admin user credentials. The access point controller can also include a powerful network processor that can provide value-added functionality, such as security and access control, VLAN management and manipulation, user roaming between access points, and quality of service. The third form of WLAN architecture is distributed architecture, also known as a wireless mesh. A wireless mesh can be used to create a dynamic network in environments where cabling would be impossible. For instance, this type of network is used by U.S. military forces in field operations. In a wireless mesh network, data is repeated over wireless to neighbor nodes, not all of which were connected to the wired network. Like a network of routers, the devices make forwarding decisions to get the data through the network as efficiently as possible. Now let's look at the standards that enable wireless LANs. Wireless LAN technology dates back to the 1970s. However, widespread use of wireless LAN technology was prompted by the adoption of IEEE 802.11 standards in the late 1990s. In addition to the original standard, many extensions have been added over the years. We can refer to them collectively as the 802.11 group of standards. The 802.11 group is actually only responsible for standards at Layer 1, the physical layer, and a part of Layer 2, called the Media Access Control sublayer. At the physical layer, the 802.11 group of standards defines a variety of different connection types for wireless links of up to 100 meters for indoor connections or 500 meters for outdoors. The original standard, released in 1997, defined a physical layer operating at a frequency of 2.4 GHz with speeds of 1 and 2 megabits per second. The 802.11b extension to the standard allowed higher wireless speeds of 5.5 and 11 megabits per second operating in the 2.4 GHz band. This specification was the first to be marketed as Wi-Fi, and it gained widespread use. A common problem for the 802.11b wireless, as well as the original standard, was interference from microwave ovens, cordless phones, and other devices operating in the 2.4 GHz range. Frequency hopping spread spectrum, or FHSS, and direct sequence spread spectrum, or DSSS, modulation were used by these standards to control interference. The 1999 802.11a and the 2003 802.11g standards increased wireless speed to 54 megabits per second at 2.4 GHz and at 5 GHz frequencies. The new OFDM modulation technique also further reduced issues with interference and increased the stability of wireless connections. In 2009, the 802.11n standard introduced a multi-input, multi-output physical layer which uses multiple wireless signals to greatly increase the amount of bandwidth that can be transmitted simultaneously. 802.11n has the potential to take connection speeds up to around 600 megabits per second. The 802.11ac standard, which is expected to be finalized in 2014, is expected to allow wireless connection speeds of 1 gigabit per second. The standards at Layer 2 primarily control who may use the wireless channel at any point in time. The primary access method is Carrier Sense Multiple Access Collision Avoidance, or CSMA-CA. A wireless client cannot detect collisions while it's transmitting, so it relies on receiving positive acknowledgments from the access point to confirm that data was received. This is slightly different from CSMA-CD, which we saw in a wired example earlier. CSMA-CD relies on detecting collisions when they occur. Let's see how CSMA-CA works. As we saw in the wired example, the client first listens to determine whether anyone else is transmitting. Each network device can either transmit data or receive data, but not both simultaneously. Only a single client can actually transmit at any one time. So if someone else is already transmitting, a client will wait to send data. Data transfer is always asynchronous, and acknowledgments are used to confirm the delivery of a frame. If the client does not receive an acknowledgment, it will back off and then retransmit the data. In addition to CSMA-CA, there is also an option with 802.11 to do virtual collision detection by using Request to Send and Clear to Send messages. In this case, the client must receive a Clear to Send message before sending data. This message is broadcast to all clients in range. We'll look at how this virtual collision detection system works in a little more depth later in this section. 802.11 also defines the option to use a centralized access method that requires an access point to pull all of the connected clients on a regular schedule to see if they have any traffic to send. In this situation, the client sends data when pulled, if it has data to send. In addition to CSMA-CA, virtual collision detection, and asynchronous data transfers, other important specifications at this layer control security. So access control authentication and encryption, roaming between access points, power save specifications, and quality of service. The generic 802.11 frame format is shown on screen. As you can see, it's longer than the Ethernet 2 frame. As we saw earlier, before the start of every Ethernet 2 frame, there is a preamble, which is used by communicating devices to determine the beginning of a new frame. 802.11n introduced an even shorter preamble called a greenfield preamble. In an environment that has no legacy devices, using the shorter greenfield preamble can increase throughput. However, at present, most 802.11n devices operate in mixed environments with legacy devices. This means that they must send both the greenfield preamble and the legacy preamble so that all clients on the wireless network understand that someone is about to transmit data. Take a moment to explore the other fields in the 802.11 frame. Click each field to learn more. As we mentioned a moment ago, the frame control field conveys, among other things, the type of 802.11 frame. There are three main types of 802.11 frames: data, control, and management. Data frames include regular data that is being transmitted and certain types of special messages intended for the access point. Control frames are things like request to send, clear to send, and acknowledgement frames. Management frames include things like beacons sent by access points to advertise the wireless network or probes sent by a client looking for a particular wireless network. Click the Additional Information button to learn more about the different types of 802.11 frames. Here are some common types of data, control, and management frames in 802.11. Let's discuss how a client finds and associates to an access point in a WLAN. First, the client must find an access point to connect to. A client may locate an access point passively by just listening for access point beacons. Or this may occur actively by probing for a particular network. Any access point on the specified network will respond if it is available for connections. If multiple access points on the same network respond, the client will typically choose the one with the strongest signal. The client then sends an association management frame to the access point. The access point responds with an association ID, accepting the association. The client is then on the network and may send data. If the client must roam to another access point, it will send a reassociation request. For the client to roam successfully within the network, the new access point must respond with a new association ID. If the client had incoming data queued for it in the old access point, the data may be forwarded across the distribution system to the new access point and then delivered to the client. Just like in a wired Ethernet environment, once a client is connected to a wireless network and ready to send data on the wireless segment, traffic is subject to collisions. In the wireless LAN environment, the hidden node problem can cause collisions. This problem can occur when there are two clients on either side of an access point which are within range of the access point, but which can't actually hear each other's transmissions. In this situation, both clients may listen to the channel, hear no data, and believe the channel to be clear. They then simultaneously transmit data. This causes collisions at the access point, which is unable to interpret either signal. In busy wireless environments with widely dispersed client devices, collisions such as this may cause bandwidth to drop as much as 40%. Neither client will receive an acknowledgement. Both must back off by a random interval and try their transmissions again. Wireless LANs have a couple of methods to help in these situations. First is the standard CSMA-CA method you've seen here. The other method available in 802.11 is virtual collision detection, which requires the use of the request to send (RTS) and clear to send (CTS) control frames. Wireless networks can be configured to use this method for frames that are larger than a certain threshold. The client first listens to determine if the channel is clear. If it is clear, it sends a request to send and specifies the duration it expects to require to send its data. Every client that hears this frame will know that it has to wait before attempting to access the channel itself. The access point responds with a clear to send, confirming the duration value. This solves the hidden node problem because even if client 2 can't hear client 1, it will receive the broadcast from the access point. Client 2 will not send data for the specified period of time. After the specified time period, the channel is available again on a first-come, first-served basis, and client 2 can now send its data. Some bandwidth is lost to overhead traffic by using request to send and clear to send frames. However, the pros of using this mechanism outweigh the cons in dense user environments. As we've seen, to ensure the reliable delivery of data across a wireless channel, under normal circumstances, every frame or fragment is positively acknowledged. If the acknowledgement is not received, the frame or fragment is retransmitted. There are a number of frame control settings that can have an impact on the reliability of connections. The RTS threshold can be used to specify a size of frame above which the request to send, clear to send mechanism must be used. Retry counters specify how many times a device should try resending a frame before discarding it. A different value can be set for frames smaller or larger than the RTS threshold. The fragmentation threshold specifies what size of packet should be split into fragments, and the fragment lifetime specifies how long fragments should be kept while waiting for related fragments to arrive. There is a lot more to wireless LANs, including coverage, security, sensitivity, capacity, and other planning aspects, but these are beyond the scope of this course. For more detailed information, view the WLAN Fundamentals e-learning by clicking the link on the screen. Here's a chance to review some of the concepts you learned in this section. As we saw earlier, unicast addresses identify one specific device. Multicast addresses are associated with a group of devices, and the broadcast address goes to all devices. Do you remember how to recognize unicast, multicast, and broadcast MAC addresses? Drag each address below into the correct box. Incorrect matches will bounce back. Well done! Remember, multicast addresses always begin with a 01. Click Continue to move on to the next screen. Earlier in this section, you performed a simple exercise to understand bridge behavior. As you know, switches operate in essentially the same manner as bridges, but have enough ports so that each port can be dedicated to a single device, instead of being shared. Here's a similar exercise in which you can apply your knowledge of MAC address tables and switching behavior. Use your knowledge of switch behavior and the MAC address on. We've covered many different devices in this section. Here's a chance to see if you can remember the characteristics of each device. Each device below is associated with a characteristic, but only one of the associations is valid. Click the box that correctly identifies a characteristic of the device shown. You have 10 tries. How many correct answers can you identify?